spectrometer. Okay, these are the instrumentation you try to come in our department. We also have the AS in the department. Okay, here these are the, I can't say, this is not very properly. Okay, I'll show you later. So this the atomic absorption spectrometer, introduction, invention, working principle of AS, instrumentation, interferences and correlation methods, applications. Okay, so this all it is included here. As you know, that introduced in 1955 by Alan Walsh in Australia, firstly used for mining, medical, okay, and treatment and agricultural and all that. Okay. And the properties of AS, the most widely used method in analysis of elements. Please switch, mute yourself. Some noise is coming from your side. So the most widely used method in analysis of elements based on the, you see in the, if you look at the periodic table, large number of the elements can be detected, but not all. Remember it, not all. But large number of the elements will be detected or will be determined with the help of this AS. It's a very sensitive technique up to the PPB level. PPB means? Any of you?
Parts per billion.
Parts per billion, but how much? In terms of?
1 gram per liter. 1 milligram per liter.
Milligram per liter? Who said? Tell name.
Enamul Haq.
Huh? Enamul Haq. Anybody else? 1 ppb is equal to how much?
ppb.
He said,
Sir, ppb is microgram per liter.
1 microgram per liter.
Checked through net. Nowadays, no, internet is helping a lot. Immediately check it. Isn't
Someone
it?
is sitting.
Not in the class, no. Online other advantage is also there. Any question is asked, immediately you check with your internet. Isn't it?
Yes.
That's good. So an exam also is very easy these days, no? Online exam is very good. This time I will give questions, okay, for like a open book exam.
Time so tight.
Time, yeah, that's why I'll give open book exam type questions. You open
Yes,
any
sir.
book, any internet, whatever you like, you open it, and you have to answer it. All right?
Yes, sir.
It's okay.
Sir, but it is very tough to maintain time.
Yes, that's why I'm telling now. So, I will give questions in such a way which answer you won't get in your notes or your PPT or your internet or whatever you use. You won't get the answer.
Yes, sir.
If you have understanding, then only you can answer. All right?
Yes, sir.
Don't make it so hard, sir. Don't make it so hard.
Why? Because it is at your home, no? So it's no problem. You have internet, no?
Sir,
You have all materials also.
Sir, we don't have any material.
Internet is there. You have very fast internet, no, than me. Anyway, let's go. We'll see that. So this is the very sensitive parts per billion, means that microgram per liter. Milligram per liter is the ppm. Okay, remember it. Always try to remember milligram per liter is not exactly equal. Okay, almost equal, because the density of the water is almost 1. That's why we say almost equal to. All right. So, and ppb means that microgram per liter. Okay, that low level you just see. Someone said 1 gram per liter. 1 gram per liter is very high concentration, very, very high concentration. Okay. So ppb means that microgram per liter. In 1 liter microgram, okay, 10 to the power minus of 6. You just imagine, in 1 liter 10 to the power minus of 6 gram. So that is the ppb level. Okay, that ppb level it can be detected. Quantitative analysis. Okay, Working principle is very simple. Electrons promote to higher orbitals for a short amount of time by absorbing energy. Say M is there plus H nu, M excited, M star. Okay. And once this works based on the Beer-Slamber's law. As I said, A is directly proportional to the concentration, or A is equal to ABC. We used to write A is the molar absorption coefficient and all that you all know. Okay. This is the simple graphical presentation: ground state and then the excited state. Now this is the instrumentation, as I already told you, okay, earlier. There should be a source. You can see here, this is the radiation source. Okay, in fact, this is nothing but this is the hollow cathode lamp. This is the, you know, where you are atomizing. These are the atoms are atomized. Okay, here is the you know, this is the flame. You can see here, this is the flame, and through this some process is there that I told you, that is the nebulization process. Through that the sample is introduced. Okay, through this nebulizer we try to introduce in this region, and then they are getting the kind of the vapors. Okay, atoms are being formed here over this the flame, and this, you see, the radiations are coming out and they will get absorbed. The same radiations that you have produced using the same element which you are going to analyze, and that will be absorbed here. And then here is the wave selector and detector, amplifier, signal processor and all that. This is the electronic devices by which you are trying to get the, you know, the signals. So this is the whole simple way of understanding of the instrumentation. Now light source, as I told you, how this light source is created or the assembled. This is nothing but the hollow cathode lamp. Okay, hollow cathode lamp, it is the, you know, there is a tungsten wire, as I said. This is the anode, and the cathode is made from the element of the interest. That means that the element which you are going to detect, so using the same element, the cathode is being formed. Okay, is being fabricated. Now this is again one disadvantage, that suppose you want to analyze calcium, so hollow cathode lamps should be made by the calcium. Suppose you want to analyze the cadmium, you have to make the hollow cathode lamp by the cadmium only. So now the thing is that for each element you have to change the cathodes. Okay, if 20 elements you want to detect, you have to change 20 times the cathodes, means that it takes time. So this is one of the disadvantage of the AS, that the number of elements you are going to analyze, that many number of the cathodes are required, hollow cathode lamps are required. So this is one of the disadvantages, that takes time also. Suppose in 20 elements you are analyzing in water samples, means that 20 times you are changing, 20 times you are making calibration and all that, it will take maybe hours to complete the whole analysis. Okay, so this is the disadvantage, but anyway, cathode is made by the same element. And then the argon or the neon gas, okay, this is the inert gas we used to keep inside. This is the hollow cathode lamp. You can see that there is an anode and there is a cathode. Neon or argon somewhere around 1 to 5 torr. The pressure, okay, there is a quartz window. Through this the radiations are coming out. Okay, so this is the you know, they are connected with the power supply, and this has been high voltage has been applied here. Okay, there is a glass shield outside of this cathode, and there is a window, through that the photons are coming out. Okay, so this is the light source again. Okay, charge lamp, typically argon gas, narrower line. So this is very important, that the line which has been produced here, okay, the photon line, it is much, its width is much narrower than the absorption line of that element. And this is okay. Atomization process that take place. Compounds making up the sample are broken into free atoms. High temperature is necessary. Basic two types: flame atomizer or the electrothermal atomizer. Okay, either of the way we used to, but very common is the flame atomization. Okay, flame means that on the high temperature we used to atomize it. Okay, types of the atomizer: simple, the simplest atomizer converts analyte into free atoms of vapor phase, flammable caustic gases, not has an inert medium, short analysis time. Okay, these are some of the advantages. Types of the atomizers: electrothermal is not that important. Okay, monochromators, okay, is also called wavelength selector. Select the role of this, the, the single wavelength, okay, that we try to monochromator with that. Okay, there is a monochromator by which the single wavelength we try to collect it. A polychromatic light is converted into only the monochromatic light. Simple one is enough for the AS. And then detector is the, I have not taught you about the photo multipliers and all that. Okay, so this is the amplifying the signals. Okay, it's not important in this course. Okay, otherwise I can explain you how this photo multiplier photo cathodes are there, that we call it the diodes. With that diodes we are multiplying the electrons. Okay, in fact what we used to do, the signal we are amplifying with the help of the photo multiplier tube. Okay, in which the n number of the, or I can say that large number of the diodes are there. With that diodes we are enhancing, multiplying the electrons. Okay, you can see here, and here the one, the four, sorry, here this is the light source, say UV. This is a kind of detector. Okay, if this light is coming here, what happens, there is a cesium or the rubidium atom which are having the low electron function. Okay, so with the small energy, okay, or the UV or the visible range of the energy, they can eject the electron. That electrons on the cathode, that will be, sorry, anode, that will be collected. There are the, the diodes are arranged here. You can see one diode is here, another diode is here, third diode is here. Through that, what happens, the number of the electrons which are ejected out, that is going to increase, and okay, and going to multiply. That is why it is called as the photo multiplier tubes. Okay, so here at the end of this, you will find that very large number of the electrons are ejected out. Those electrons are counted here, and then you will be the signals you are getting here. So with this, with the help of photo multiplier tube, the only advantage is that a small signal, okay, which may not be detected, but at the end you can see here large signal you will be getting. So that is why it is called as the multiplier tube. Okay, so this is amplifying, and then you will be getting the good signal here. Okay, so calibration we used to do by a simple method. Okay, that is the, as I said, A is directly proportional to the concentration. Through that we try to, so for that, calibration curve method or the standard addition method. Okay, these two are the, basically in analytical chemistry we used to do this analysis based on the calibration. We used to do either by the calibration curve or by the standard addition method. Standard, sometimes they call it the standard dilution method also. Okay, so but standard dilution method is not that common. Standard, this calibration curve is very common. How does it work? It is a very simple. Okay, draw a curve, have two or more variables. One is set known value. Okay, one is measured response. Most convenient, large number of the similar samples. Okay, let me to show you. Okay, this, how does it work? You just take the with this curve, I can tell you, and tomorrow again I will be taking another the class. In that class I will be telling you about that, the least square fitting method and all that. Okay, there I will discuss more. Here you see that it's a very simple. A is directly proportional to the concentration. You understand this? This is very simple. A is directly proportional to the concentration. B, since we have already fixed it. Okay, if you increase the concentration, here you see what will happen, absorbance is going to increase, isn't it? All right, this I think there is no problem. If you increase the concentration, the absorbance is going to increase. What we have done, you can see 0.2, 0.4, 0.6, 0.8 and 1 milligram per liter of the sample concentration, you have increased it. Accordingly, you can see that initially the absorbance was here. When you have increased, the absorbance has increased here, then increased here, and increased here. And this will be a straight line because A is directly proportional to C. That is the straight line equation. Y is equal to mx, isn't it? Y is
Yes, sir.
equal to mx. So that means that the A is directly proportional to C, or A is equal to B, A, B, C. That is the straight line equation. Okay. So now B, since B is a constant, now you see that here you can draw the straight line. Once the straight line is drawn, so the slope you will get it. Means that A is equal to ABC, A is equal to ABC means that C is constant. Okay, A is the molar absorption coefficient or whatever you say, okay, or extinction coefficient if you say, and C is the concentration. Extinction coefficient, it is for a some particular element, it will be a constant value. Okay, A is equal to, I can write here, A is equal to, okay, ABC, no? This is A, this is B, okay, this is C. C is the path length. This is a constant. If this is a constant, again, you can write it as A is equal to A into B. Okay. Say B is, if I write it as B, nothing but it is the concentration C. Okay. If this is C and okay, this, just a minute. If this is a concentration C, okay, and B is the path length. So in that case, in this equation, A is equal to A, B, C. If C is the concentration, okay, B is the path length. If path length is constant, okay. So in that case, what you will be, you can write A is equal to A into C, isn't it? A into C. C is the concentration. All right. Now you see that if you increase this C, A is going to increase. And this is a constant, okay, and this is the slope. A is dependent to C, all right. A is dependent of C. If you increase C, A is increasing. Now from this equation, okay, you can see this equation. This is called as the calibration equation. Okay. Now what we do, a known concentration of the analyte we increase, and the absorbance, correspondence absorbance we try to measure, and we draw the calibration line. Once you draw the calibration line, the slope you can simply get it from this line. This slope is now known. Okay, if A is known, which is a slope for this element, and if the unknown sample you take it, its absorbance you try to measure, slope is known, you can calculate C. Any problem? If A's absorbance you are knowing, okay, slope you are getting through this calibration line, C you can calculate it, isn't it? Because A is a constant.
Yes,
Okay, so this is called as the calibration technique. Or otherwise, you can see if this calibration line is drawn, if suppose absorbance is this much, suppose this absorbance is coming here. So the corresponding value of the concentration, you can get it here, isn't it? You will get the
Yes, sir.
concentration here, whatever concentration is here. Same thing you will be getting either using this equation or by this calibration line. Okay, you can get the unknown concentration. So this is the basic principle. Either you are doing the UV visible spectrometer, or you are doing AS, or many other are there. Okay, similar way it works. Okay, so this is the way of the calibration technique, is called as the calibration technique. Okay, standard addition method is there, that is not that important. Okay, we used to add the standard concentration, okay, known concentration and all that is not that important. Leave it. So as I mentioned initially, the interferences are there. There are the 3-4 interferences, okay, causes higher or lower absorbance value. The major groups: chemical interference, spectral interference and all. Okay, as I mentioned, spectral interference, that suppose the element you are atomizing, it is not atomized and forming some the oxides, and that oxides also giving you the same wavelength. Okay, the you know, at the same wavelength they are absorbing the light. In that case, okay, this is going to hamper, okay, your element to be detected. So this is and the some more, the most I already told you I will try to send you some notes also if possible tomorrow. Okay, whatever I have, in your the book. If you remember that the GD Christian book, you can follow it. Okay. Anyway, tomorrow I'll try to send you the notes also on this WhatsApp group. The most common one is the flame atomizer. Consequence of the chemical reactions, reduce amount of oxygen in the flame to overcome. Okay. Spectral interference, absorption or emission of the radiation at the same wavelength. As I said that initially, if oxides are being formed and or the similar other element is also absorbing, okay, in the same radiation, same wavelength, radiation which is absorbed, positive errors, radiation which is emitted, negative errors. So spectral correlation, two-line correlation, this is not that important. Okay, the correlation, this is not that important. Okay. So the conclusion is that one of the most important technique in quantitative analysis, it is based on the absorption of the radiation. Measurements could be done at ppb levels. It is widely used method. The preparation of the sample is usually simple and rapid. You have to make a clear solution, otherwise you cannot analyze. Always you have to make the solutions. Okay, usually we have to digest it properly, then only you can analyze it. So conclusions, there are many advantages. Okay, the high sensitivity, as I said, 10 to the power minus of 10 grams to 10 to the power of minus of 14 grams, non-flame type. Good accuracy, relative error is 0.1 to 0.5%. High selectivity. Okay, the applications are there. Water analysis is widely used for the water analysis. Okay, for many elements to be detected. Food analysis, food samples, in that the trace elements and all we try to analyze. Analysis of animal feedstuffs, okay, in which magnesium and many things. Analysis of the soil also, that you can do it, but as such the soil you cannot analyze it, you have to digest it. Okay, you have to make a clear solution. Okay, clinical analysis, blood samples, whole blood sample, plasma, and this thing in which the elements can be detected. So these are some of the references and all that. So that's all. Okay, now is you just